This is module M5G of the Indiana Department of Transportation Certified Asphalt Lab Technician Program. And this section is entitled How to Do an Asphalt Mix Design. So there are several steps in the process of doing an asphalt mix design. We will talk about these steps individually. They are contract specifications. So these are the specifications that we will try to meet. The selection of materials that we would do our design with. The selection of the aggregate structure, or in other words, the trial blends. The batching and compaction of a trial blend. Evaluation of a trial blend. The determination of what should be our final aggregate structure, and then lastly, the selection of an asphalt binder content. So the first thing about doing a mix design is that we will end up submitting it to INDOT for approval. And in order for us to be able to do that, we have to be an INDOT approved laboratory. So if we have not gone through the approval process, that is a requirement to submit a mix design for INDOT. So we need to get that done. Now, in terms of what specifications, AASHTO specifications that are used, it is basically AASHTO specification R35 that is being used to do the mix design. Now, in terms of the contract specifications, we will find in the Indiana Department of Transportation specifications, in section 401, we will find information about what is referred to as QC/QA HMA, quality control, quality assurance, hot mix asphalt. In section 402 deals with HMA, which is usually used for local agencies or can be used for very small quantities on an INDOT project. Section 410 deals with SMA, stone matrix asphalt. This is a specialty type of mixture that is used predominantly on high volume roads, or basically the only place you will find it is on high volume roads. Regarding the materials, asphalt binders are specified in section 902 of INDOT specifications, and aggregate requirements are in section 904. The information about which specifications apply is embedded or encoded into the item description. So there will be QC/QA HMA, comma, and then there will be a space for EASL, and it'll be EASL category 2, 3, or 4. Next space will be for asphalt binder grade, and it will be the PG high temperature. All the asphalt binders in Indiana are -22 grades for the low temperature grade, so that's not specifically shown, but it's inferred. The next blank spot will be the course that this mixture is to apply to. Is it to a wearing course on the surface? Is it an intermediate course? Or is it a base course? That mostly will have an impact on aggregate properties for some surface courses. And then the last open space is for the mix size, the nominal maximum aggregate size. So an example would be QC/QA HMA, 2, 64, intermediate, 19 millimeter, meaning this is for EASL category number 2, which is a low volume mixture. PG grade 64 minus 22. It is for an intermediate course, and it has a 19.0 millimeter nominal maximum aggregate size. So the easel categories are 2, 3, and 4, with 3 being less than 3 million easels, as I mentioned earlier, low volume. 3 being sort of a middle of the road, 3 million to 10 million easel, and 4 being anything greater than 10 million. Many state highways are going to be category 4 mixtures, and some of the lower volume state highways will be between 3 and 10 million. And there are a few areas where you'll find INDOT highways that have or mixtures that will require less than 3 million, but it's not so common of a mixture. Now, the mixed design criteria are given in the section 401, and it's specifically 401.5. There is gradation specifications that are given for dense graded mixes, for open graded mixes, and there's a table for each of them. The gyratory compactive effort is specified, the voids in the mineral aggregate that we need to achieve, and the voids filled with asphalt. The aggregates are specified in section 904, and the requirements for fine aggregate angularity, or you can think of that as crushing in the fine aggregate, coarse aggregate angularity, which is crushing in the coarse aggregate, and then surface aggregates, meaning friction type aggregates or aggregates that are wear resistant for high traffic conditions such that they will maintain their friction values for wet weather stopping conditions. So in selecting our materials then, the easel category is going to tell us as a mix designer what compactive effort do I need and what are the requirements for fine aggregate angularity and coarse aggregate angularity. The coarse, base, intermediate, and surface, the only impact that this has is whether if it happens to be a surface material, depending upon the easel category, will tell us whether we need friction resistant or friction maintaining aggregates. The nominal maximum size is typically related to the lift thickness, but that's a given to us in terms of what nominal maximum size we are to use, and then of course the asphalt binder grade that we are to use. So there's how we select the materials that we will use in putting together our mix design. So we obtain the materials and lab samples of the materials of the different aggregates. There you can see the wrap down in this area. They're showing here a compacted specimen, and they've taken some asphalt binder and poured it down onto this piece of paper so that you can see the asphalt binder. So in terms of selecting our aggregate structure, what we will do is we will establish the trial blends. And this is going to be an exercise that says on paper, meaning in an Excel spreadsheet on the computer. Then we will select which of those trial blends we want. We could do one or we could do more than one. And we'll batch and compact those, and then we will evaluate those trial blends. In regards to gradation, from the specification, here is the gradation chart, and you can see that in our example of a 19 millimeter, it requires 100% passing the 25 millimeter sieve, Our blend has to have 90% to 100% passing the 19 millimeter sieve. The 12.5 millimeter sieve has to be less than 90% in our blend. There are no specific requirements for a 9.5 or 4.75 millimeter sieve size. On the 2.36, we need to be between 23.0 and 49.0. And then once again, on the one, there are no specific percent requirements on the 1.18, 600, or 300, and then on the 75 micron sieve between 2 and 8%. For open graded mixes, we have a minimum and a maximum on most of the sieves. For the open graded 9.5, there are no requirements on the sieves that are below the 2.36 until you get all the way down to the 75 micron sieve. Also, asphalt content is specified. There is a minimum percentage of asphalt that is specified for the open graded mixes, that it is an explicit percent, as compared to for the dense graded mixes, where there's not an explicit percent, but it is determined as part of the mix design process. So we put together our trial blends on a spreadsheet, and we select percentages of each of the different materials that we propose to use, and we're looking for our combined gradation to be within the specification limits that are set for that material. Now, mix design is all about how aggregates behave, specifically how they pack together. So let's talk about what is it that controls how aggregates pack together. The number one thing that will control the packing of aggregates is gradation. The shape, the texture, the angularity of the aggregate particles will influence how they compact together as well. Now, the compaction, the type and the amount of compaction will influence how the aggregates pack together. And then lastly, the hardness of the parent material. So let's look at these and evaluate what options do we have for controlling the packing of the aggregates in terms of doing a mix design. So the first thing to think about is the hardness of the aggregate. If I have a relatively soft limestone, what can happen is that my aggregate particles, some of them will break during the compaction process, and it will allow the aggregate skeleton to pack tighter together than it would for the same gradation and all the other things being the same, but with a harder aggregate. But most of the time, I don't have a choice of choosing the hardness, meaning that the company that I work for has entered into an agreement or has bought aggregates from a certain quarry. Those aggregates meet the specification requirements of the DOT, and the company has decided that those are the aggregates that I am to use in my mix design. The fact that I could maybe have an easier time doing a mix design with harder aggregates is really immaterial. It's not a choice that's available to me. So I can cross hardness off the list of options that I have available as a mix designer to affect the packing of aggregates. But what about compaction? The type of compaction is gyratory. The number of gyrations is specified based upon the type of mixture. Therefore, compaction type and amount is not something I have available to me. Now, what about shape, texture, and angularity? Well, I have some flexibility here. For example, there is a fine aggregate angularity requirement, and which is basically crushed faces on the fine aggregates. And I might have available to me natural sand and manufactured sand. And normally I might use a blend of those. I can, by using, if I wish to have more particle shape, texture, and angularity, I can use more of the manufactured sand and a little less of the natural, or vice versa. I could use more of the natural sand and less of the manufactured if I want less angularity. If I want, and of course, the shape, texture, and the angularity will influence how tightly together the aggregate particles will pack. So I have some flexibility there, but I have constraints because I have to meet this fine aggregate angularity requirement. Same thing happens if I have, gravel, which doesn't have so many crushed faces, perhaps, and crushed stone. I can elect to use a blend of those two for some of the mixes, but oftentimes I will just use crushed stone because my coarse aggregate angularity, my crushed faces on my coarse aggregate requirements are high enough that I really don't have any flexibility there. So what is the main thing that I have to control the way aggregates pack together? Gradation. That's it. I am looking for a gradation of this specific set of materials such that when they are compacted with the type, the gyratory compactor, and the amount, the number of gyrations, that I end up with the right amount of space, the desired amount of space in between those compacted rocks. And what I have to control that with is gradation. So let's talk about how gradation influences the way that aggregates pack together. Now, before we talk about aggregates, let's talk about spheres, balls. So what controls the packing of balls? So if I had a room and I wanted to fill it up with basketballs, what I would figure out, and I went and I got a whole truckload of basketballs to do this with, or more than a truckload if it's a big room. And I would find that the best way to put the basketballs into that room would be to arrange them in rows, and then each alternating row, I would offset the balls such that it falls halfway in between the two in the row before it. And so I would make a layer of balls using this method. Now, when it comes time to make another layer of balls on top of that, I would place this ball right where these three come together and kind of create a divot where that fourth one can sit on top of. And so the next ball that I would place would be on top of these three, and the next one in this direction would be on top of these three, and the one here would be on top of these three. So that would be the tightest packing of balls. That would allow me to put the most number of balls into a room. Now, in terms of percentage of the room that is full of balls, it turns out it's about 75%. In other words, about 25% of the volume of the room is these little spaces between the balls. Now, if I did this same experiment, but I used baseballs instead of basketballs, it turns out that the percentage of the room that I could fill with baseballs would be identical to the percentage of the room that I could fill with basketballs. And you might think, hang on, that doesn't make any sense. Baseballs are a lot smaller. They ought to pack tighter together, not? And the answer is, well, yes, they are smaller. As a result of them being smaller, these spaces between the balls will be smaller. However, the number of balls in the room for baseballs, the number of baseballs in the room will be much larger than the number of basketballs. So when I look at it in regards to percentage of the room that is full of balls, they end up being the same. Same thing happens if I was to use golf balls. Same thing would happen if I use marbles or BBs. Now, you might say to yourself, you know what? If I wanted to fill this room up with more than 75% volume of balls, what would happen if before I put a basketball on top of these 3 basketballs, I put a ball down here and I bet you I could put a baseball there. And if you thought that, you would be approximately correct. A baseball will sit down in that space such that I can put a 4th basketball on top of here, and that basketball will still touch these 3 basketballs, but that baseball sits right in the middle there. And not only that, I could put in some golf balls and some marbles and some BBs. And if I did that and I played around long enough, figuring out by trial and error what is kind of the blend of basketballs, baseballs, golf balls, etc., such that I get the most percentage, the highest percentage of that room full of balls of different sizes, it would end up being about 90%. I could fill up 90% of that room with balls of different sizes. Now, if I said to myself, I wonder when I fill up that room with 90% balls, what percentage of them are basketballs? What percentage of them are baseballs, golf balls, marbles? And I put this picture in just to kind of show, the packing, the style of packing that this is. So if I did that, I would find that 100% of the balls would be basketball size and smaller. About 50, I think that's 57%, would be baseball size and smaller. About 45% would be golf ball size and smaller. Marble size and smaller is about 29, maybe almost 30%. And BBs, which I don't have a picture of a BB on there, is about 18, 17%, something like that. And I'd have this curve. By the way, that is a real set of data. Those are real numbers. If you wanted to put those sizes of balls, I looked up the sizes of the balls and I did the calculation to calculate that. Now, if instead of making a plot of the percent smaller than a certain size versus the diameter of the balls, if I did this based upon the same plot, but based on the square root of the diameter of the balls, I would get a curve that looks like this. It would be a perfectly straight line going from the largest size ball, basketball, which I think is about 10 3/4 or 10.8 inches in diameter, all the way down to BBs here. And that line would go through this origin point right here. Now, for rocks don't pack together quite the same way that balls do. This line is a straight line on a graph of the square root of the diameter of the balls. Another way of saying square root of the diameter is to say the diameter raised to the 0.5 power. When this experiment is done with rocks, and it was back in the 1930s or thereabouts, they took half-inch size rocks, quarter-inch size rocks, 1/8 of an inch, a 1/16 of an inch, a 32nd of an inch, a 64th of an inch. I think that was the smallest one that they used in this experiment. And by trial and error, they figured out what was the blend of rocks that gave them the tightest packing. And they found that if they made a plot kind of like this one, but instead of plotting the percent smaller than the ½ inch against the square root of the diameter, or the diameter raised to the 0.5 power, it actually worked better because rocks are not balls. It worked better with the diameter of the rocks raised to the 0.45 power, and hence the origins of what is referred to as a 45 power chart. So in hot mix asphalt in North America, this is not true in Europe, they use a logarithmic chart, but in North America, we always plot gradations on a 45 power chart. So what happens is, if you look at a gradation chart, you never see a scale that says 0, 1, 2, 3, 4. So for example, the number 4 sieve, which is 4.75 millimeters, 4.75 millimeters raised to the 0.45 power gives a number 2.02. So what happens is, if we make a vertical line here at 2.02 and label it number 4, and then not show this horizontal axis, then we get a gradation chart. And that's exactly the case here. So you can see there's the number 4 sieve, and there's 2.02. And if you look on most gradation charts, like paper ones, if you see any paper ones, you never see that scale down on the bottom. And by the way, that's the reason why in Excel spreadsheets, we end up having to put together some macros in the background so that we can create a 0.45 power chart, because it's not a standard function in the list of tools that come with Excel. So the AASHTO specifications are built around a 0.45 power chart. And although this maximum density line, which would be the gradation that will give you the tightest packing of the aggregates, is not part of the specification, it's kind of hidden in the background. So let's look at the different parts of this AASHTO gradation specification. So the first thing that we'll look at is these 3 control sieves up here. And they are defined by, they are reference to the nominal maximum size and the maximum size. And they are defined by the nominal maximum size as being 1 size larger than the first sieve to retain more than 10%. Now, that sounds almost like circular logic. So what we have to do is, in our combined gradation, we look for the first sieve to retain more than 10%, and the nominal maximum size, according to AASHTO, will be 1 size larger than that. So in a 12.5 millimeter nominal maximum size, the first sieve that in our blend that will be less than 90% will be the 9.5 millimeter, and then 1 size larger than that will mean that the nominal maximum size is a 12.5. The definition forces the gradation always to be between 90 and 100% on the nominal maximum size. The maximum size is defined as 1 size larger than the nominal maximum size. So most of the time, this will be pretty straightforward. In our case here, that would be 100% passing the 19 millimeter and somewhere between 90 and 100% passing the 12.5. But there is a special time when we can get fooled. This is when it is. Let's say that we have a gradation that is 80% passing the 9.5. So what's the nominal maximum size? Well, the first sieve to retain more than 10% would be the 9.5. So the nominal maximum size is 1 size larger than that. So it's a 12.5 millimeter nominal maximum size. Now, what if the percent passing the 12.5 is 100%? Well, the nominal maximum size is still 12.5, and the maximum size is still 19.0, even though there is no material between the 19.0 and the 12.5. So be careful that you don't get fooled that way. It doesn't just go to the sieve in our blend that has 100% passing, because depending on what the nominal maximum size of our blend is, then it will influence what the maximum size is. Okay. Next, let's talk about these sieves. So this is the primary control sieve. And in the AASHTO specifications, it actually sits on it is one sieve. It's in a table in AASHTO M323. And it's one sieve that sits right on that maximum density line. That's how it was chosen. There is a maximum and a minimum on this primary control sieve. So let's talk about a couple of different things. First of all, how did they decide which sieve size should be the primary control sieve? That was done based upon the nominal maximum size of this gradation chart. So for a 12.5 nominal maximum size mixture, where I have 4 12.5 millimeter rocks, 1, 2, 3, and then a fourth one to go on top. And of course, rocks aren't all the same dimensions. They're not like balls. So, you'd have to do it with a bunch of sets of 4 rocks. But on average, the largest particle that I can put amongst those 4 half-inch size rocks is going to be a number 8, or a 2.36 millimeter size particle. If I try and put a 4.75 millimeter particle in there, that fourth one not going to come down on top of it. Okay? So that's how the sieve size is selected to be the primary control sieve. Now, why did they decide to put this primary control sieve on that maximum density line? Let's look at, and I think for a 12.5 millimeter nominal maximum size, this is around 40%. So if I had a gradation that is 35% passing the 2.36 millimeter, it means that 65% of the material is bigger than that, 35% is smaller. In that 65% of the coarse aggregate, there is room for the 35% of material to fit in there. So what does that mean? That means that by and large, the properties of this mixture are controlled by the coarse aggregates, meaning it is a coarse graded mixture. Now let's look at a gradation where we have 45% passing that primary control sieve. In that case, we have 55% larger than the 2.36, 45% smaller than the 2.36. There is not enough room in that 55% coarse aggregate for 45% of the mix, the fine aggregate, to fit inside. So as a result, there will be numerous places where the smaller size particles are going to be holding apart the larger size particles because there's too many of the small size particles. So that is a fine graded mixture, meaning that the fine aggregate will play a larger role in controlling the properties of that mixture. It will be a fine graded mixture. So that is how they decide where to put this primary control sieve. The next thing that we'll look at in the gradation specifications is the percent passing the 0.075 millimeter sieve, or the number 200 sieve. So there's a narrow range, and there's just a minimum and a maximum. And basically, the controls on this is if we have too much dust, that it will suck up the asphalt binder and turn the mix to being kind of gooey and dry. And if there's way too much dust, it'll actually change it from being a black mixture to a chocolate brown colored mixture. And if there's not enough dust, then there's a risk of the mixture looks very rich because there's no dust mixed in with the asphalt binder. And during storage in the silos and transportation in the trucks, the asphalt binder can have a tendency to drain down off of the larger size aggregates. So that's why there's quite a narrow range between the minimum and the maximum on the number 200 sieve. So here we can see 3 trial blends. All of them are course graded, and they all go below this primary control sieve. And the thing to note about them is that there's not nearly as much room to change the gradation here as there is in the sieves between the primary control sieve and the nominal maximum size. The gradation has to go between 100 and 90. In this case, it's a 19 millimeter nominal maximum size. And you'll notice that the primary control sieve is now 4.75 millimeter. It's bigger than the example that we just looked at. So we can put together trial blends, and typically if we are wanting to do a course graded mix, we would put together trial blends that are all course graded. If we wanted to do a fine graded mix, we would put all the trial blends to be above this primary control sieve. So our next step is to prepare the aggregates. Now that we've put together blends in the computer, now we're actually going to prepare specimens. So we get our aggregates together, and the first thing that we need to do is our stockpile blend, our stockpile of aggregates. We need to sieve it down to different sizes so that we can separate each stockpile into a number of different sizes. And then when we batch our specimens, we will batch them according to these different sieve sizes. So we will put together for ourselves a batch sheet, and we will end up determining the number of grams for each of the stockpile blends for each of the fractions of the stockpile, and we will batch together our specimens. When we batch together the specimens, then we will put them into a pan along with some cans of asphalt binder, and we will heat all of this material up. At the same time, we will heat up the mixing container and the mixing hook that we will use to prepare our compacted specimens. So here you can see after everything is hot, that here's our mixing container, and we put the aggregates into it. We've calculated how many grams of asphalt binder do we need to add, and we add the asphalt binder to it. Now we put the bucket and the mixing paddle onto the mixer, and we allow it to mix until it is well coated. And then we put it back into a pan. Now it's going to go into the oven for short-term aging. And that short-term aging is 4 hours. That allows for asphalt binder to be absorbed into the mixture and although it does not, what's the word I'm looking for? There can be the asphalt binder absorption will decrease with time. By the time we get to 4 hours, it's mostly stabilized. it can still increase a little bit, but not that much. So 4 hours is what INDOT requires the mixed design be. And here you can see the sample. They put it in a non-stick paper, and then they folded the sample over top of it, and they wrote some information on top of it. Here you can see the gyratory molds. They put it in the oven to be heated up at the same time that the sample is sitting in there and short-term aging. After the 4 hours, we take our sample out of the oven, we take our mold out of the oven, and we're ready to charge the sample into the mold and compact it. We're going to compact it in a gyratory compactor, and in the specifications, it will tell us the number of gyrations to be used. For the lowest volume, it's 30 gyrations. For categories 3 and 4, it's 50 gyrations. Now, this gyratory compactor places the mold on an angle, and it's been calibrated such that the internal angle inside the mold is 1.16 degrees, and there's a plus or minus on that as part of the calibration process. And there's a vertical pressure of 0.6 megapascals. That's about 90-ish psi. It's about the tire pressure of a truck tire, maybe not quite. And it gyrates or rotates at 30 gyrations per minute. And the mold is just a little less than 6 inches in diameter. It's 150 millimeters. Then what we are going to do is, or not we, but the machine is going to monitor the compaction process by continually reading the height of the specimen as it gyrates. And what that means is we will be able to determine the bulk specific gravity of the specimen after we take it out of the gyratory, after it's been compacted the 30 or the 50 times, and we've allowed it to cool off, determined its bulk specific gravity of the compacted mixture. And then we can actually, knowing the height of the specimen at that point, and knowing the height of the specimen at any gyration, we can actually get a gyratory curve of density versus the number of gyrations. And we can get a curve that looks something like this. And on a scale where it's the percent of the maximum specific gravity on the vertical axis versus the logarithm of the number of gyrations, these are approximately straight lines. And so we can get these plots, or the software can make these plots for us. So let's say that we've done this for 3 different trial blends. Now what we will do is, for those trial blends at end design, we will measure the bulk specific gravity and the maximum specific gravity of the mixture. From that, we are able to calculate the percent air voids, and with the bulk and the maximum specific gravity, plus the asphalt content, we are able, and we also need to know the bulk specific gravity of the aggregate, we are able to calculate the VMA, the percent VMA. Now, maybe by luck of the draw, we were lucky enough to exactly hit 5.0% air voids. Probably not. We probably came somewhere in the ballpark of it, but not exactly it. And so we can estimate the asphalt binder content to achieve 5% air voids for our trial blends. And then we can estimate the mixture properties for each of the trial blends at a new asphalt binder content. We can estimate the properties of the percent of maximum theoretical at the N initial and at N design. We can estimate the dust to asphalt ratio, and we can compare all these estimates to the mixture criteria. So this is how we are going to evaluate which, if any, of these 3 trial blends will provide a suitable mix design for us. So the aggregate, the thing to remember is that the blend of aggregates and the way they pack together is going to control the VMA, and the air voids are adjusted with the asphalt content. So if the VMA is acceptable, then it's a matter of changing the asphalt content to determine to get it to the right air voids, and that then we can determine the asphalt content, or design asphalt content. So let's say that these are our 3 trial blends. And from gradation 1, we ended up with 6.4% air voids and 17.3% VMA. Trial 2, 4.9% air voids, 15.4% VMA. Trial 3, 4.9% air voids, 16.4% VMA. Now, the specification that we're trying to meet is 5% design air voids and 16% VMA. The trial blend, the gradation, controls the VMA. So let's look. We need a 16 minimum. We have 17.3. That meets the minimum. Now, not only does it meet the minimum, but it exceeds the minimum by more than a comfortable amount of what we might want to design. And generally speaking, mix designers will target somewhere around perhaps 0.5%, 0.75% above the minimum. And this is 1.3% above the minimum. So it's really too high. So trial 1, not really very acceptable. Trial number 2, 15.4% VMA. It's too low. So this blend of aggregates is not going to work for us. So we discard trial 2. Trial 3, 16.4. Okay, so that's just a little bit above. I said, 0.5%. Well, it's 0.4%, so it looks pretty good. And the air voids ended up being 4.9%. So we can do an estimate at 5%, and we can guesstimate that the voids filled will be about 70. The spec is 60 to 70. That's not bad. The percent GMM at N initial needs to be less than, or a maximum of, 91.5. Our trial blend, we estimate 87.4, so that's less than 91.5. That's good. So the dust to asphalt ratio needs to be, and this is dust to effective asphalt ratio, needs to be between 0.6 and 1.4. We would estimate that we will end up about 1.01. That's good. And our VMA at 5% air voids, probably going to be exactly where it is here with this asphalt content at 4.9%. So, and that's above the minimum. So trial 3 looks good. Let's go ahead. And now our next step is to, well, hang on here a minute. So the first one, the VMA is too high. Second one, the VMA is too low. So both cases, we need to change the aggregate blend. Trial number 3, the VMA is okay, so that aggregate blend should work just fine. So now what's our next step? Our next step is to determine the optimum asphalt content, and this will be the asphalt content at 5% air void. So we're going to take the trial blend, the gradation that we have, and whatever the asphalt content that we estimated to be the optimum, we're going to do a blend mix that's got 0.5% more asphalt binder, 1% more, and 0.5% less, 1 point that's below our estimated optimum. So we're going to have at least 3 points. Sometimes designers will do 4 points, pardon me. Then we're going to create graphs of the mixture properties for the different binder contents, and we're going to select a design asphalt content. So here's our 3 points that we did, and you can see that at 5% air voids, it looks like we're at about 5.9% asphalt binder. So at 5.9% asphalt binder, what is the VMA? And so we come up here and we look, yeah, and it's about 16.4. So that meets the spec. That's good. At 5.9% asphalt binder, we're right smack dab on 70% voids filled. That's the upper end of the specification limit. It meets the specification, so that's good. The percent GMM at N initial, we need to be below 91.5, and we are here at about 86.5. So that meets the specification. So all those properties meet. So 5.9% appears like it's going to be an acceptable asphalt binder content for this mixed design. Now, we're not quite done yet. There's 2 more things that we need to do. The first one is that there is something called N-max. So we design the mixture at N design. N-max is a higher number of gyrations. So at the 5.9%, which is our estimated optimum binder content, we need to prepare 2 specimens and gyrate them to N-max. Also, we need to evaluate this mixture for moisture sensitivity, for tensile strength ratio, TSR. When we do all of that, and we have a final mix design, then we're ready to report on our mix design sheet our submittal for INDOT. So there's the asphalt content that we got. There's the air voids that we designed at, and there's the VMA. It ended up being 16.5, and the VFA ended up being 70.0. And so all our properties are listed on here, and we have a successful mixed design. We're ready to submit our mixed design to INDOT for approval. And that's the end of this section dealing with how to do a mixed design.